This is the fourth day of the CSAE conference. It is our agriculture day, and this is in our second agriculture session of the day. We are going to talk about infrastructure and agriculture. I'm Doug Gollin from Oxford University, and I'm going to chair today's session. Let me just give you a little bit of a general guideline to what's going on. Daniele Rinaldo is going to talk about dams and their impacts. And then Tilmann von Carnap is going to talk about market access, so affecting agricultural expansion and intensification. So those are the papers that we'll have. It should be a great session. So on that note, and without further ado, I'd like to turn things over to our first speaker, which is Daniele Rinaldo from Cambridge, who's going to talk about market access. So Daniele, over to you. And I will probably give you a 5-minute warning, a little more than 10 minutes in.
Thank you so much. Good morning, everyone. It's a great pleasure to be here and to be presenting my work titled Dams, Snails, and Poverty Traps. So, yes. So just a couple of slides to put the paper into perspective in terms of what it aims to do. We've seen in dramatic force in recent times how economic systems can be made vulnerable to the presence of disease. And in particular, the states in which a disease is both widespread and persistent are called the endemic states. And these endemic states are prevalent and particularly harmful throughout the African continent. And this is the starting point of this paper. In particular, I will focus on the endemic state generated by a disease you might not have heard of, called schistosomiasis, also known as snail fever. You might not have heard of because, in fact, it is a neglected tropical disease. It is waterborne, meaning that the way that the parasites that cause the disease are transmitted from the ecosystem to the population are snails that live in freshwater basins. So with this small introduction, I will present the objectives of this paper. First of all is to estimate and identify the economic burden of this disease via its effect on agricultural production, with an empirical focus on the country of Burkina Faso. We can imagine why this burden should be large by means of the effect on agriculture, especially in the sub-Saharan region, where, and in particular in Burkina Faso, where agriculture is employing 80% of the population, and most of which of a subsistence variety. The second objective is to study and to exploit the waterborne nature of this disease in the study of the feedback between the disease dynamics and water resources development. So dams, hence the dams in the title, and water irrigation networks. Why? Because especially in the regions where this disease is endemic, and particularly in the sub-Saharan region in Burkina Faso, water resources are possibly one of the most fundamental measures for poverty reduction, meaning that they are one of the most sort of substantial ways to exploit, development finance and foreign aid. However, such infrastructures, whilst boosting agricultural output, they also boost the vector suitability of this disease, the snail. And this kinds of feedback effect is what I want to study in this paper. Lastly, I want to find the evidence for the presence of poverty traps generated by this disease. The way I want to establish this is on a joint empirical and theoretical perspective. On the theoretical side, by means of the creation of a bioeconomic model, which is rooted in my empirical findings and fit to data, to study the nature of this trap and to study the economic nature of the endemic states. So with this in mind, a quick slide on why should we care as economists on this particular disease. From the health perspective, it is very prevalent, even though it's neglected. You see more than 250 million people. It is treatable, but there's no vaccine, and reinfection is continuous, so making it hard to eradicate. The health effects are debilitating and lifelong, the ones you see in the slide, but particularly the real burden here is borne by children in terms of stunted growth, anemia, and cognitive deficits. We know there's a large literature on how shocks to childhood health can lead to lower wages and lower labor productivity. And this is where the economic eye enters the question, because this disease is widely considered to be labor impairing and poverty reinforcing, even though evidence so far on this has been mixed. And which is surprising, especially because it's widely thought that the patterns of transmission of this disease is tightly related to anthropic factors, so man-made factors, dams being a fundamental one of these. And this is just to show the prevalence of the disease in the African continent. And you can see it particularly in the sub-Saharan region and in the country of Burkina Faso, which will be my empirical focus, whose borders you see highlighted in white. Now, a couple of slides on the data set that I use. It's one of the contributions of this paper, which joins existing data with recent developments in disease mapping. On the existing data side, I have a large panel, which is the Enquête Permanente Agricole, the EPA, collected in Ouagadougou, which is fundamentally a large panel with detailed data on yields, pesticides, crops, and the like, as well as demographics on households. What I do is that I geolocalize and merge all of this together and geolocalize precisely villages, 2,500, which correspond to roughly 20,000 farming households. So fortunately, quite a bit. The second part of the data set is that I collect this data on water resources, which is the 4 main dams, very large infrastructures for hydroelectric purposes mainly, as well as spatial data on irrigation networks. I will show the map later to put this into a visual perspective. And lastly, it's satellite data on climate rasters taken from daily data to create yearly variables, seasonal variables, a vast array of covariates to absorb and to exploit all of the possible sources of variation given from climate and environment. And the new bit is the disease data, which is what it looks like. I have 2 maps, which are fundamentally corresponding to large-scale Bayesian logits. What are these things? These are done by just statisticians, by epidemiologists. And what they take is that they take survey data, which is by nature very spotty, especially in disease, and they create high-resolution estimates of the prevalence of this disease in children. This is particularly important. This is new. This is something that could not be done before. And this is important because it allows to exploit the wealth that we have from the survey data sets and study the burden at a household and plot level. So this is the data that I use, and this is how the data set looks like. Think of this as different stacks, one on top of each other. The A is the villages. Of course, the households are not identified geographically, but these are the villages that I have. B is the water resources. The big ones are the large dams, and the small ones are the middle to small irrigation networks. You can see that there's quite a bit of them, allowing to exploit a lot of variation. And C and D are the 2 maps of disease that I have. This plot generalizes and explains the mechanisms that I study in the paper. And the main mechanism of interest is number 1, which is the effect that's caused by schistosomiasis on agriculture, conditioned on the covariates I have in the data. So plot, household, climate, and land. So because of a variety of issues, unobservables, measurement error the most, but a vast array of possible concerns, the other mechanism is the Snails, from the title, which is the spatial density of the intermediate host of the disease, which is used as a set of instruments, which is mechanism number 2. The other 2 mechanisms is the mechanism of poverty trap, seeming that, especially in sub-Saharan Africa, you can imagine that shocks to agriculture of subsistence are direct causes of poverty, hence it's a poverty-inducing shock. The point is whether a greater state of poverty also by itself amplifies the magnitude of this burden, and this is what I want to find out. The last one is the role of dams, so number 4, which we know, this arrow you see on the right, that this is one of the main sort of boosters of agricultural production. However, they also boost the suitability of these snails. What I want to find out is then to net out these 2 sort of contrasting effects and get, in a wider sense, to establish returns to such infrastructures that account for a wider set of environmental externalities. Now, a bit on the results. So the empirical framework is, what I find is that I identify, and I find that it's compatible with this specification, is that the debilitating nature of the disease is akin to a productivity shock, meaning that it is not the input use at the optimum that is affected by the burden. However, it is the way that these inputs are utilized. So in a way, Higgs neutral, one could say. And therefore, the identification that I have and the way that I find it's compatible with the specification is that yield, so output per hectare of plot I at time t, household H in village J, is defined by productivity shifters, a production function, F, fluctuations, log normal, most likely, and this burden, which is this term here. Why is it modeled this way? Because if phi, the disease burden, is 0, then we collapse to a standard production function. And the more the burden increases, the more the way that inputs are utilized is affected, is adversely affected. This is the idea behind the specification. Now, there's a lot of potential issues, of course. First of all, that phi is not observable. And it's proxied from the maps, which are at the village level. So measurement error, all kinds of endogeneity is a possible concern. So the spatial density of the intermediate hosts, the snails, is used as a set of instruments. Of course, there's much more to this, which I would be happy to discuss without the time constraints. And this yields a structural equation of this form, which is time, household, and crop fixed effects, a production function, so a production frontier that once is structurally estimated and identified, it allows to identify this parameter theta as the real parameter of interest, so the burden of the disease on agricultural production. And the way that I identify this production function is twofold. There's the standard Cobb-Douglas assumption, which allows for the usual set of techniques. However, another way that I approach this is that I use adaptive methods, so machine learning techniques, to identify adaptively the shape of this frontier without having to specify it, partial it out, and get a precise estimate of interest of this parameter theta here. And this is what is done, and this is the set of results that are presented now. Top is Cobb-Douglas, bottom is the adaptive. And first of all, it's significant, and it's negative. The box in the parentheses is for readability. Outside the parentheses is the burden, so the loss of agricultural yield caused by the schistosomiasis for the households that experience a median level of disease. So the median loss, I could say. In parentheses is the loss experienced by households at the top 5% infection quantile, so the ones that suffer the worst, in a way. And we can see that it's substantial and negative, which is between 8.9% and 6% average loss, which becomes a whopping 43 to 32 for the ones, not so many, but the ones at the very top of the infection quantile. So this is the first result. So establishing this burden as a productivity shock that harms agricultural production. This effect is non-linear, as we see in the bottom panel, and it starts to be negatively significant around the first tercile of intensity. So having established this, it's important to see the role of water resources. You can see on the right, it's the map of all the dams. And what I do is that I study double and triple interaction, which is intuitively, how does this burden I change as villages are further away, 1 kilometer away and more, so per kilometer away from these infrastructures. The triple interaction means how does this burden change as distance increases when the infrastructure is one of these 4 large dams you see in the figure with the name. And if this dam is, this indicator is 0, we have the double interaction, which is the distance from reservoirs when the reservoir is one of the small triangles you see in the figure. This requires spatial techniques for a variety of reasons, and on the left is the distance between villages as spatial weights. And what do we find? We find that villages adjacent to the large dams experience a substantially higher loss due to the disease, meaning that, in fact, the presence of these dams is, of course, beneficial. It's also one of the results that, of course, it is beneficial, is around 25 to 30%. However, the loss, the incremental loss caused by the presence of the presence and increased resilience of the ecosystem of this disease, in fact, drastically reduces such infrastructures. And as villages move away, the triple interaction here on the right, in fact, decreases the burden, meaning that one must add 1.5 to minus 20, meaning as 1 kilometer, as villages move away 1 kilometer, the burden is reduced by 1.5%. Something a bit more hopeful is the fact that this distance effect does not seem to be the case for smaller irrigation networks, which has a lot of potential implications.
Daniele,
please.
Just to give you a kind of generous 5 minutes ahead. All right.
Thank you so much. Some quick evidence on the presence of poverty. And what I study the incremental effect of households at the lower tail of a poverty distribution. This is a household level indicator, a distribution of the households that farm the least amount of yield and the smallest amount of crops jointly. And seeing whether there is an incremental effect. And there seems to be the case. In fact, the lowest tail has a 45% loss, which is substantially higher, 32 for the 10%. This is an indicator of a potential loop akin to a poverty trap. But in order to understand whether this can actually happen, there's a theoretical framework to understand what could be the driver of this potential negative, or this sort of vicious loop. And this is, I will not present the equations, but I will just give the idea behind this formalization. And it's a dynamical system of farming households together with the ecology, the equations that drive the diffusion of the disease. this has the advantage of using all my empirical results and, for example, seeing the identification of the disease burden as a productivity shock to the production function as a structural assumption for this model, which is then fit to data. Now, what are the key findings? I will present only the most relevant for this presentation, which is, first of all, that endemic states are Nash equilibria, which are not social optima, meaning that the fact that the disease is so prevalent in an economic system, it's because, in a way, trajectories are attracted towards the steady state, which is absolutely suboptimal. In fact, is completely Pareto dominated by the rest of the equilibrium. And the reason why a poverty trap can emerge is that the disease reproduction rate, we're more familiar with these terms nowadays, is dependent on the level of wealth, so on the poverty condition of the system underneath. Other results is the roles of mobility, fluctuations in information, which I will be not presenting. But just to summarize the results of the implications of the model is that this R naught is the key element that defines the persistence of this equilibrium. Now, if this R naught is less than 1, we have that the economic resilience of the system is drastically superior to the ecological suitability of the disease. Imagine this as, for example, Europe, that this disease could be introduced, schistosomiasis could be introduced, but because of the structural qualities of the system, this cannot be sustained. As this increases, we go more towards the structural form of sub-Saharan countries, and Burkina Faso in particular, where we have two sets of conditions: the household-related conditions, so the strength of the production possibilities, which are juxtaposed to the strength of the suitability of the ecosystem that can foster this disease. And these are coupled. Therefore, if we have a weak economic system and a strong suitability of an environmental system, then we have the creation of a poverty trap. In this case, formalized as a fully attracting equilibrium, which is characterized by high disease, low wealth, and low consumption. And this is what seems to happen. And this is what is actually being able to map to the scenario and to the data that I have. And this is why we have a persistent state. And the dams actually play a role in this because they keep boosting increased suitability whilst, boosting the ecological suitability whilst also boosting economic resilience, but not as much as to balance out the presence of this trap. So just to summarize the overall findings of the paper is this burden generates an estimated loss of slightly less than 1% of GDP, which is quite high. And this poverty trap is generated by the higher R naught. Now, the question is to be asked is, in terms of inequality, is who is actually reaping the benefits of such large water infrastructures? Is it the villagers around? It doesn't seem to be the case because these are mostly built with foreign money, but also built with irrigation purposes, so for large cities, whereas the villages around seems to only reap the negative externalities generated by such infrastructures, meaning that from a policy perspective, reinforcement of the middle and small irrigation networks seems to be of paramount importance. And on the policy side, given that the economic burden is substantial and poverty reinforcing, needs to be concentrated in the parts of the countries that have the upper two terciles of disease intensity in order to be most effective in terms of reducing the burden of this disease. And that will be all. Thank you so much.
Fantastic. Thank you so much, Daniele. Really interesting presentation. And thank you too for sticking to a very short amount of time. There's already a question or two popping in. We'll come back to the questions at the end. Again, to those of you in the audience, please do type your questions into the Q&A. We will take note of them and ask the speakers to address the questions when we get through the three presentations. So I think what we'll do is just move right on into the third presentation. Our third speaker is Tilmann van Carnap from IIES in Stockholm University. And Tilmann, over to you.
Thank you, Doug, and thanks everyone for joining. I'll be presenting joint work with Anna Thomset at the Department of Economics here in Stockholm, and Paul Christian and Astrid Swacher at the Development Impact Evaluation Unit at the World Bank. And in this project, we're looking at a sort of third kind of rural infrastructure. We heard of electrification and water access. Now I'm going to look at the effect of road access, in particular how market access through roads affects agricultural intensification using remotely sensed evidence from Mozambique. Our study is motivated by two common observations in developing countries. First, that agriculture productivity has been and is still low across many of these contexts, and that rural road infrastructure is often poor or unreliable. Now, we know from sort of model-based research using household data that high transport costs are a key factor in hindering the technology adoption that could increase agricultural productivity, and that these high transport costs indeed are a factor in reducing incomes. So this has led, well, this forms the base of large policy interests among donors and government to invest in roads, in road infrastructure. But the evidence that we have on the effects of these programs is actually fairly limited, and also with mixed results. So across a set of contexts and a set of studies from Nicaragua, India, and Ethiopia, we find that one of the main effects on how roads affect rural economies and their transformation is that they give access to labor markets, so that it allows people to access opportunities for non-farm employment in the area that they would otherwise not have reached. We also know that roads, in order to be effective, may require complementary investments in electricity or in extension to farmers, so providing additional knowledge to farmers. One of the few studies that shows an immediate effect of roads on technology adoption in agriculture is from Shamdasani in India, who shows that it's actually the most remote regions that do not have access to these urban labor markets where this sort of specialization in agriculture takes place. So we want to add to this literature with evidence from another context, but a highly policy relevant one, and looking at a specific agricultural outcome, namely land use. So to motivate our specific study or our specific approach a bit further, I would argue that one of the reasons why we have such limited evidence on rural roads programs is that there are two distinct challenges in analyzing these programs. First of all, roads may be built to areas that are expected to grow anyway, so attributing any effects to these roads may be fraught. And roads are expensive, so they're usually built in small numbers, so we don't have a lot of variation to play with. Furthermore, when it comes to agricultural outcomes, it's fairly rare that agricultural data is collected consistently over time and space around these road projects, with the notable exception of the programs in Ethiopia that I mentioned in the previous slide. So what we do to make progress on this is that we don't focus on the rollout of a particular road program, but we rather look for very local variation in market access. In particular, in our context, it's going to be due to river crossings that are unreliable. Now, at these river crossings, the basic idea is that when this crossing is not passable, I cannot reach the market on the other side of the river. Now, there's no big household survey around these rivers at the moment in Mozambique in the context we're looking at. So we're going to use satellite imagery to measure a set of agricultural indicators. In particular, we're going to focus on three indicators. First and foremost, the share of available land that's used for agriculture. And then within the area that is used for agriculture, looking at measures of plant productivity, similar to what Gitika presented earlier. And using these outputs that we generate, we can also look at land management practices, such as the frequency of land conversion. So let me tell you a bit more about the context we're looking at here and explain our identification strategy. So the context of the study are two provinces in northern Mozambique that are larger than England, and home to about 11 million people. And in this area, agriculture is the mainstay of the economy, but poverty rates are high and above the average for the country. Farmers usually grow crops without a lot of additional inputs, so irrigation and fertilizer use is very low. And the crop mix is focused on the staples that are usually sold locally. Now, this region is also characterized by a rather sparse and vulnerable road network. So the road density of paved roads is only a fraction of that of, for example, India. And farmers indeed state that this lack of transport is one of the reasons that makes them sell only locally. A particularly weak point of the road network are these river crossings. So on the right here, you see an example where the river would flow from sort of bottom left to top right here, and the road should go over this structure. But even though there's not a lot of water in the river right now, the whole embankment has been washed away, and so it's basically impossible for a vehicle to cross this road at this particular point. We do not have evidence on which particular crossing is, or we do not have data on which particular crossing is unusable at a particular point in time, but we can see from high-resolution satellite imagery that about a quarter of crossings in our sample and in this area are damaged at any point in time on average. This means that like these roads may be repaired, or it may be possible to cross the river when there's no water in it, but especially during and after the rainy season, these access constraints may be binding and are found to be binding. So to find these crossings, we used GIS data, starting with the road network in this area and intersecting it with a map of rivers in the area. Now, this is an area that has a lot of precipitation, but fairly concentrated in time during one major rainy season. So this means that we cannot just rely on sort of visual identification of rivers, but we want to even identify the areas where rivers flow only seasonally. And for this, we use a digital elevation model that lets us find areas where water should accumulate and flow towards the sea. So this gives us the sample of about 700 crossings here marked with these small black icons. And we identify about 700 of them, and they are typically fairly small. So up to 25 meters, or around 25 meters is the median width of the rivers. And as I said, it's common that they are dry rivers, as the one on the right during the dry season. Now, the gist of our identification strategy is going to be comparing two banks that differ, two banks of the river that differ only by their access to markets. So if you imagine that there was a city down here, then if I'm a farmer on this bank of the river that's here shaded in green, I don't care so much about whether this bridge is functional or not, because I can just travel to the market anyway. But if I'm a farmer up here, then if this bridge is broken, it may be very costly for me to get to this market, or at least more costly to get to any market than it is for people on this side. So we want a measure of which bank of each crossing is relatively advantaged or disadvantaged by this particular crossing. And for this, we use a measure from the trade literature, where we estimate market access as a weighted sum of the product of travel times from my location to a set of population centers in my region. We then derive outcomes at a high resolution, a 10-meter resolution, which is going to be important in our context, because as you can see, this is an area where sort of the landscape is not only dominated by agriculture, but there are like interspersed groups of trees or grassland that is not continuously farmed. We aggregate these outcomes in these distance buffers along the road, which are going to be the units of observations for the study. So what is the data that we're using here? We derive it from optical Sentinel-2 imagery. It's a program by the European Space Agency where you can access these images free of charge. And the basic idea here is to, given that, as I said, the landscape is so unstructured, so not purely forests or not purely agricultural, we want to be able to distinguish between these two categories very clearly. So what we do is to train a random forest classifier on the time series of these images over one agricultural cycle, where we give the algorithm training data on what are agricultural areas and what are natural areas. We do this per district and only keep those districts where we have a sufficiently high accuracy. And in the sample of districts that we keep, the accuracy is 83%. So in 83% of cases, the algorithm correctly assigns a pixel to the category of either being a pixel either being agricultural or a natural area. This outcome we can measure over 3 agricultural seasons, and we plan to extend this period. Now, within these areas, we can look at a vegetation index over the parts of the agricultural cycle and use this time series for the frequency of land conversion and the duration of fallowing periods. To give you an idea of how this looks and the granularity of this data, in the top left here you see a raw image from Sentinel-2, which happens to be partly cloudy and here masked in pink. But we can composite these images by a chosen time period, here 6 weeks, to get these cloud-free composites. And having those composites over the year gives the algorithm information to distinguish very locally between land that's used for agriculture in red or land that's used for, or that is not used for agriculture here in green. And then finally, within these fields, we measure NDVI. As secondary data sets, we use a dataset compiled by the Facebook Data for Good program, which gives house density across the country and indeed across the African continent at a 30-meter resolution. We access a database of fires, which are a common land clearing practice in the area, and we check for the covariates of soil organic carbon, elevation, and rain around these crossings. So how do we estimate the effect that we're interested in? As I said, the basic idea is to compare outcomes at a crossing within a narrow area around this crossing, depending on whether you are on the close side or on the far side. Now, there are 2 challenges to this. First of all, there may be a lot of variation in land use that's related to the rivers itself, independent of market access, that would overshadow the effect we're trying to measure. For example, areas around the river obviously have better access to water, and this like very locally around the river, and this may overshadow the main effect we're after. So
I'm just going to interrupt enough to let you know that roughly 5 minutes,
sure.
Soft 5 minutes.
Thank you. So to control for these factors that are related to the river but independent of market access, we introduce fixed effects for the absolute distance to the river, and which also include a fixed effect for each crossing. But we may also worry that there are broader spatial trends broader spatial trends in general in the region that are also present around the crossing. So, for example, land is more likely to be used for agriculture the closer you get to cities. So we want to make sure that our market access measure or our ranking using this market access measure doesn't just pick up these differences. For that, we have 2 approaches. First of all, we fit local trends on either side of the bank in terms of the distance to the crossing on this residualized outcome measure from above. And secondly, our inference strategy explicitly asks how different spatial trends, or how different agricultural outcomes are around the crossings compared to any other set of locations. So we look at we reconstruct p-values by asking how likely would I have been to observe the difference that I see at the crossing at any other set of points along these roads which do not have rivers. Let's have a look at the results. This is a bin scatter plot of the residualized outcomes, or the residualized measures of agricultural land use for the whole sample of crossings and for a subsample of crossings along unpaved roads and in the vicinity of markets. So on the y-axis you have the residualized measure, that's why it's centered around 0. And on the x-axis you have observations arranged by their distance to a crossing, where if you're on the close side of a crossing, your distance is measured negatively here, and if you're on the far side of a crossing, your distance is positive. So you can basically read this as a city being somewhere here and a river crossing being here. As you see, there's a general spatial trend that intuitively shows that land is more likely to be used for agriculture the closer we are to cities. But there's also this shift at the crossings particularly so at roads that are likely to show this. So in this context, these are unpaved roads, more likely to be flooded or washed away in areas that are relatively close to towns, so above median, close to towns. We find indeed that this difference is significant, and not just statistically, but as we would argue also economically. So what does this mean? This point estimate means that land on the close side of crossings, so in this side here, now focusing on this area within 1 kilometer, not 5, but 1 kilometer around the crossing, is 2.6 percentage points more likely to be used for agriculture, which is a sizable effect on the base of land use of 49% of land for agriculture. So what does this mean? It would suggest that if these crossings were all perfectly passable, then we shouldn't see this jump because these banks are comparable. So one of the responses we would expect to improve market access via reliable crossing would be a higher share of land used for agriculture. Now we can go a bit further than that and also look at whether the land that is used for agriculture is managed differently. Here I'm showing the results for NDVI, where our starting point was sort of that, well, more productively managed fields or more intensively managed fields should have higher NDVIs, as this is a common interpretation of NDVI. However, we find that areas that are further away from towns in general have higher values of NDVI here, and it doesn't seem to be affected by the river crossing in a statistically important way. Indeed, we don't find significant results here. How do we interpret this? Well, this is a context where irrigation and fertilizer use, which would make fields more green, is very uncommon. So adoption rates of fertilizer are below 10% and below 3% for irrigation. So the main adjustment here could be in field management. So when you farm more intensively closer to towns, you sort of make sure that your field has less undergrowth or is more clearly delineated from your neighbors. This would fit the general spatial trend here, but we don't find that this is a response directly at the river crossings. We also look at whether land is more or less likely to be frequently converted around the crossings. And here we find that a slightly confusing result for now, that areas on the close side of rivers are more likely to be converted from fields to natural land, but this doesn't necessarily indicate a higher frequency of turning land from fallow to used, because we don't see a mirrored effect for areas being converted from natural to fields. We also don't find significant differences in fires as a measure of land clearing practices. In terms of the previous literature that looked at labor migration as a response to market access, we don't see this here, at least not in the sense that people shift their houses over these crossings in order to be closer to markets. So to conclude, we find that the intensified use of available land may be the main response to improve physical market access in this context. And river crossings here are really an economically significant barrier to intensification, which suggests that upgrading programs may want to focus on these particularly vulnerable parts of the road network. We don't find evidence, however, that land here would be managed differently. To sort of link this to some of the previous literature, why do we think that road impacts on agriculture would differ across contexts? Well, first of all, a remote region in India may still be quite different from a remote region in Mozambique in terms of access to markets, in terms of access to inputs. And they may, and clearly the outside option matters here. So whether, or in our context, access to or opportunities for non-farm employment are still very rare. So more reliable access to those may not matter very much, but rather people would focus on agriculture. Going forward in this project, we plan to start a survey, COVID permitting, that would validate our land use classifications and the market access measure that we use. And in the more long run, we want to track the impacts of a road upgrading program that actually will build more bridges and more roads in the area using some of the methods we have developed here. So I'll close with that, and I look forward to any questions you may have. Thank you.
Thank you very much, Tilmann. Great presentation. So I'd like to open things up now for Q&A. We have a number of questions in the Q&A, and I think what I'd like to do is to go through the questions that are there. And I would still, while we're handling those, encourage people in the audience to add more. Daniele, I have a couple of questions that are in the chat from Estelle Kouchoubé. I believe Estelle is no longer in the webinar. So let me read her questions for the benefit of the audience. She has two, and I think they're quite related. One is, could the effect of the schistosomiasis that you're observing on agriculture be due to migration from infected places outside the locations that you're looking? And I think in part, her follow-up question is, did you look at the impact of campaigns to control schisto and what happens after those campaigns in terms of migration and agricultural production?
So, great question. The role of migration directly, let's say, I'm not fully ready to talk about, migrants causing disease. So the way that I wanted to approach the issue of transmission on a network, I have done this in the paper actually, and it's extra slides which I could not present. It was framed in the way of human mobility, more than a sort of directed migration in terms of I optimize where do I go, comparing a set of, let's say, an optimization process. In brief, the answer is yes, I do look at this, and it is, what I find is that the presence of human mobility, let's say moving from smaller villages to larger agglomerates, is a driver of the disease. And this is something that has been studied in a sort of epidemiological only framework. What I do is that I include this within the economic systems, and I find that the presence of mobility simultaneously defines the poverty conditions and the disease conditions based on let's say, weight on how many people move between the different nodes on a network. So it is something that happens. It is something that is it is addressed, and yeah, I would like to put the migration aspect in this. In terms of estimation, I do not have data on the migration, so this is not something I can do with this data set. And also, the way I, let's say, my data set, I focused on a balanced panel of repeated households. So this kind of excludes migration a bit directly. If I was looking at cell phone data to try to find out the role of human mobility, but it's difficult data to obtain. In terms of the second question, which let me read again, is, wait. Yeah, the effect of the campaign to control the disease. This is something that that has been done in 2004. There's been a statewide intervention that allowed to reduce the disease. This is, it was too staggered to exploit this in a sort of in a discontinuity technique way. But what I have is that the two maps of disease implicitly include a bit of this, meaning that the second map is decreased because of the long-term effects of this eradication process. So this is included into the estimation. There was another bit, which was the, so this in terms of control the diseases in agricultural production, this is included into the estimation in terms of having two maps that absorb this phenomenon. The migration is not possible with the data set that I have, although it would be fantastic to obtain this data set. So I hope this explains the question.
Great, thank you, Daniele. I think the next question is for Tilmann, and I'm going to call on Binta Diop.
Hi, so I think one of your strong assumption, and I could be wrong, I might have understood it wrong, but is that the communities on either sides of the crossings would have been behaving similarly had there not been this breakdown in the infrastructure system. And so I guess an underlying assumption here is that landholding is binding, and that essentially you can't have people sorting on either side of the river. And so I guess my question is just, is that true that landholding is binding? And is that what's driving some of your results? Or can everybody just get land wherever they want, basically?
So we do look at whether people actually move across the crossing. So we don't find any degree of bunching on the close side of the crossing, like using this data sets of houses. Our understanding is that land in this context is sort of allocated by village leaders, and that like in these communities, and that farmers can choose how much of this land to use within the realm of the land that belongs to the community. To the extent to how much rivers delineate boundaries for this land use, we don't have direct information on it, but I would argue that since so many of the river crossings are fairly narrow, it would seem unlikely to me that they are these boundaries. So in short, I think it is a setting where farmers can sort of choose on which side of the river they want to farm, and if they have their choice, they want to be on the side, or they want to use the land that's on the side where they don't have to worry about the crossing becoming unusable later during this season.
My next question, shifting back to Daniele and keeping things going around, comes from Mattia Bertazzini. Mattia.
Hi, Daniele, thank you for this. So my question is actually a bit related to something you were mentioning before, but I was wondering if these investments in irrigation infrastructure sometimes come with a bundle of other investments, which is something you see for road infrastructure at times. So for instance, clinics or schools. And if that is the case, if you think these other investments might mitigate the negative externalities you measure, which would make me think that perhaps you might be underestimating the actual negative impact of these externalities.
That's a good question. Yeah. It might be. The largest dams, maybe in the smaller ones, in the smaller infrastructures, this could be a thing, which I could check. Definitely not for the larger dams, though, which seem to be the real culprits in terms of these negative externalities. These usually come from foreign aid. For example, China has built 3 or 4, no, actually 2 of them in Burkina Faso itself. I mean, not itself, but it sent a lot of financing for this. So the distance effect does not seem to be as powerful for the smaller infrastructures. This is why, from a policy perspective, it is important to boost these, especially if they come with extra benefits, such as clinics, as you were saying. So I will look into this for sure. Thanks a lot.
Great. Tilmann, I'm going to abuse chair's prerogative a little bit and ask a question of my own for you, which is a little bit of a policy question. I don't know if you're comfortable speculating a bit, but if I were an infrastructure funder, I might look at this rather modest effect you're finding actually on agricultural production of 5–6% and think that might be a disappointing result. If I were thinking about the impact of improving infrastructure, not just in terms of river crossings, but more generally about expanding transport infrastructure and connectivity. And I guess my question is, how do you square that, what seems like a relatively modest return, with the fact that you also find such strong effects for proximity to towns and cities, which on the other hand seems to suggest that there's quite a significant payoff to being well connected?
Thank you. I think on whether the effect we find is a small one or a large one, it's of course a key question, but we're a bit, at the moment, we're a bit in a difficult position to interpret this, because like this headline result of 5.6%, that comes from a comparison that assumes that all crossings present a constraint to transport. So as I said before, like we see that there is a problem at these crossings in about 25% of crossings at a given point in time, but we don't have a good way of quantifying what a broken road actually means. So it may be that this crossing is just not passable for a few weeks or a few days even, but people can come later. So one of the goals that we have in the future is to quantify better what the difference in market access is across the crossings, and that would allow us to to say more about whether it's a large or small effect. We have a discussion in the paper that says that the effect of being on the far side is similar to being moved sort of 10 percentile points up the distribution in market use, in land use. So there would be a sizable effect. I think what like interpreting this effect, or interpreting that the fact that the effects are concentrated around cities really suggests that maybe the highest returns to improving this infrastructure are for now to be found in areas that do have access, that are relatively close to markets already, rather than areas that, even if connected better, would still face significant transport costs. And there would be a difference too, I think, in the context in India, where areas that are remote already have a different agricultural development stage than areas that are relatively close in Mozambique.
Thanks, that's really interesting, and of course, hard to speculate always. So next up, I'm going to go back to Carol Mazer with a question for Daniele.
Daniele, so I was wondering about this interrelation between wealth and prevalence of these endemic states that I think you uncovered. I mean, I saw this on the graph from the model, but maybe I missed it. Maybe this is also empirically proven. So I was wondering whether there is any method of preventing these diseases at the local level, sort of related to previous questions, but I'm thinking about sort of decentralized efforts, whether these societies themselves, invest time into, I don't know, cleaning the water resource out of snails, or I don't know, whatever else they may do, and whether this may depend on the wealth of this local population. Maybe it's through some non-homotheticities in utility function or something like this. And if this is done in your sample, if you know this. And somewhat related, I was also wondering whether it could be a reason that you find that there's a difference between these big dams and smaller irrigation infrastructure in terms of the disease prevalence, if I understood right. So I was also wondering if there may be some issue here in terms of property rights, in the sense that maybe the big infrastructure, maybe big irrigational infrastructure is affecting many societies around, and no one really feels that they are responsible for maintaining it. And maybe the smaller projects, smaller infrastructure is more kind of, affecting one or two villages around, and they coordinate better, and they are maybe better able to address the problem, if this makes sense. Thank you.
Yeah, fantastic questions. I'll start from the second. This is actually an interesting thought that could be put in as a possible explanation. The reason of the increased prevalence, there's a lot of this is the ecology itself, meaning larger quantities of water imply larger quantities of transmission. So this is one of the main drivers in this. In terms of property rights, imagine that these large infrastructures, they're hydroelectrical, so they're not substantially aimed at the populations living around, but they're mostly for the larger agglomerates. So they're most likely to have the larger cities benefit from them. So there is an issue with property rights for sure, because when we have, for example, smaller scale irrigation networks, they're usually owned by the villages and for the agricultural production of the village. So this is something that is definitely part of the answer. In terms of the disease itself and the associated burden, it is most likely because of the size. So the fact that these dams are really large and they have really large basins of water. So I hope this answers that. But I will think about the property rights, because that's a very good point. In terms of what you said in terms of the prevention, it is connects also to the question done before in terms of the network mobility of the disease. The fact that people move around and transmit the disease makes local intervention difficult, because you can intervene locally, but then people bring it back. So this is hard to do it locally, which means that intervention must be done with at a greater level, at a state level, or let's say at a regional level, and usually is done by foreign aid. And the difficulty, the specific case is that either you remove it completely or you keep getting it back, which is why this disease is so persistent. And this is also why it's connected in terms of the connection between wealth and endemic states in this case, is because wealth is also associated with, better sanitary condition, better access to clean water and not stagnant water where the parasites are. So it's all somehow connected and then transported on a wide network of human mobility. So I hope this answers.
Makes sense. Thank you.
Great. So back to Bintazara Diop with a question for Tilmann.
Yeah, so I think, so my question had to do more with how do you think about the estimation that you're running. So essentially, if I understand it right, is that what you're looking at is what does bad infrastructure, what are the impacts of bad infrastructure when it comes to market access, right? And so I'm guessing that this could be similar to looking at exactly the same, but where a bridge was never supposed to be built. And so essentially for that, you could look at the impact of bad infrastructure versus no infrastructure at all. And so if your story is like holds, then you should have a similar idea of what's happening, right? So the bad infrastructure should still be better than no infrastructure at all. And so I think my question is basically, would it be possible to look at that to see if essentially the bad infrastructure had negative impacts overall compared to no infrastructure versus positive? And so that's kind of more of a conceptual question.
Thank you. That's a great question. So we don't have a setting here where we can look at sort of where we would have a large set of places where a bridge could have been built, but wasn't, basically because agriculture is so clustered along the roads in general. So if you go far, like if you go 2 kilometers away from the roads, it's basically only natural land in this context. But we do have an analysis in the paper that basically broadens the buffer along the roads in parallel on both sides of the river. I hope that's maybe you can have this figure in mind with the red and green sides of the river. So that looks at, are the differences that we see in outcomes most pronounced at the crossing, or are they more pronounced away from the crossing? And what we find is that they are actually more pronounced slightly away from the crossing. So in places where like you would have to make a big detour to reach the bridge, but then the further you get away from the crossing, and as I said, the more likely land is the less likely land is to be used for agriculture, these differences disappear. So we're not really in a situation again where we can say what would happen without these bridges, but if we can get a better understanding of what do these bridges mean at the moment and what could they be, or like can they actually be like a road? Like if you travel there, would you just not realize that you're crossing a river? Then we could, I think, quantify better what you are after.
Great. Wow. So we got time, I think, for one more round of questions. So Maika, I'm going to come back to you for a question to Daniele.
Yes, thank you very much. Daniele, I have sort of two questions. One is a very self-interested one, because I was wondering whether you would be willing to share your data on the irrigation maps with us.
It's already public. It's in my GitHub. Anyway, yeah.
Okay.
Yes.
Thank you. And the other question was about the migration, and not so much transmission via migration, but whether people leave the affected areas. And I was wondering whether you could possibly use the census data, although that's only every 10 years, so it might be too far apart to tell you much.
As a parallel analysis or a different paper, yes. For this specifically, I have household and time fixed effects, which would probably definitely wipe this out. So but it's an interesting thought to put this for another way of thinking of this of the impact of this disease.
Thank you.
Great. Then I think Mattia is, I think we're over to you for a question for Tilmann.
Hi, Tilmann. Thank you for your presentation. I just had a curiosity / question about heterogeneity in terms of types of crops. So I was wondering if you have looked into where your effect is concentrated, if you see a difference between subsistence and commercial crops, because I would expect more commercialized farmers to care more about their connectivity versus non-commercial farmers. And I guess, land suitability would be a intuitive way to get at that. Thank you.
It's a great point. So the dream would be to use satellite imagery to detect those crops remotely, to be able to say whether it's like vegetables or cereals. We don't have that yet. So like we don't have localized information on what crops are actually grown, but using like crop suitability maps is a really good idea then, which we haven't done. So seeing whether these effects not only differ by proximity to markets, but also by the kinds of crops that may be grown there would be a really good idea. Thank you.
Well, I think on that note, we're about out of time. And so I would just like to thank all of the speakers, thank everyone in the audience, especially those who have asked questions, but also those who didn't. I'm sure that all of the speakers would be delighted if you wanted to send them questions via email after this. I'm sure they'd be happy to hear from you. And please do pass along comments and questions. It's one of the things that everyone loves to get from a conference presentation. We are missing the chance to interact and to have coffee, which is what we'd really like to do right now. But I just want to thank all of you. A special thanks to the speakers and thanks to the CSAE